Hello, everyone, and welcome to Control Automation Day 2023. We are proud to deliver this keynote presentation from GE Digital,
sponsored by Mouser Electronics.
Energy production is a critical component of every modern society around the globe. Additionally, the energy industry sector is a major employer for many of the engineers and technicians that make up our amazing Control.com audience. But energy production presents a few challenges that can be unique, as could be said for nearly any industry. I'm excited today to learn about the innovations that are now possible thanks to emerging technologies related to this year's Control Automation Day theme, which is the Industrial Internet of Things, and the progression of all kinds of digital transformation concepts. Today we'll be speaking with Achalesh Pandey, the Vice President of Artificial Intelligence for GE Digital, to learn about the process of data and optimization and to learn about how to meet current and future energy demands. Well, Achalesh, thank you so much for joining us here for Control Automation Day 2023. We're very excited that you can be one of our keynote presentations for this event.
Thanks, David. It is my privilege to be here and share my insights and knowledge with this very knowledgeable community, basically.
Thank you. So we wanted to get started by talking just a little bit about your story and how you arrived and first got interested in this intersection of where traditional industrial automation is focused on hardware, yet industrial Internet of Things is the development of digital software. So how did you first arrive at this intersection between these two worlds?
Yeah, so I started my career with the power plants in the power generation space, and specifically in the operations, controls, and performance monitoring kind of the area. And performance monitoring was the area which basically attracted me to this field, because you have to analyze a lot of data which we are collecting from your control system, from weather, from several other places. So I was performance engineer, and then doing a lot of asset management applications also. So that was my starting point to get entry, to get acquainted with this area and apply a lot of analytics solution for that when I was working in the power plants. But my real journey in this large scale IIoT applications and IIoT started when I joined GE General Electric, basically in their research center. And there it was the Energy Propulsion Technology Lab, Remote Prognostics Lab. The goal of that lab was to collect the data from all the GE equipments, whether it is gas turbine, it is locomotives, or whatever you can name. And then we basically then apply a lot of algorithms we used to develop. We developed a lot of algorithms for non-stop, continuous 24/7 monitoring of these equipments and different aspects. It is asset management aspect, performance aspect, controls aspect. So that was my journey, basically, where I started in this field, essentially.
And that's really interesting with all of the discussion of how this is unique to energy production. We'll be talking a lot about that through our discussion today. And we're going to be splitting this discussion up into kind of three different sections of how data is collected in this industry, with first looking at detection and then looking at prediction, and then moving on to probably the most important part, which is how is it used for optimization.
Right.
So as we start talking about detection, from your experience and background in the energy industry, what sort of challenges do you see or do you know of that face these fields of energy generation and transmission the most often?
Yeah, so if you look into the detection problem, let's first go into why do we need detection? Like, we are trying to detect or predict some failure in advance so that I can avoid that unplanned downtime, and I can basically use that information to reduce my overall cost. I don't want something to fail and cause the catastrophic failure later on, or collateral damages, because these equipments are very expensive. So that's the major purpose. So key here there is how to detect or predict these things in advance with sufficient early warning. Sufficient word is very key here, because it is totally depends upon the context. Whether you want to apply this problem on closed loop controls, then you need only few seconds, or you are using it for long term monitoring, then yeah, one day may be sufficient or 1 month may not be even sufficient. So it totally depends upon that. So the key challenges in the industry are, there are not sufficient sensors. Observability is one of the big problem. Like uh, we can say that, hey, there are tons of the sensor, but many places there are not sufficient number of sensors because if you take the example of gas turbines, it is running in very very high temperature. There are not lot many sensors in hot gas path of the gas turbine, for example. So the observability is the problem, but there are some answer to that. You utilize some of the physics based modeling approaches, where you can calculate the virtual sensors by running the heat and mass balance analysis, find out those, and then feed that information to machine learning or AI capabilities, which are very good detecting the pattern, and then doing the performing some of the root cause investigation also later on. So that's the one problem. Observability is the problem. Second problem, if you really want to apply some of the machine learning AI kind of the capabilities, then you need to train your models, these machine learning, on, you have to teach it on a lot of data. We call it supervised learning, basically, where you are feeding various kind of the failures to it, and then it will learn that about that failure, how to predict that failure. Unfortunately, in our industry there are not many failure, otherwise we will not have that kind of the high reliability. We will not get the power all the time. So how to do that? That's another challenge. There are some solution to that. Is okay, you use unsupervised learning approach, where you don't have those failure data, but you have tons of the normal operation data. So you train the model on the nominal data, and you learn about the nominal operations, and whenever something is deviating, then you are saying that, hey, I am finding some pattern has changed. However, you can't flag for every single anomalous behavior. It can be driven by operational behavior and other, so it generates a lot of false alarm. Then now you combine that information with some of the physics knowledge, some of the domain knowledge, to mitigate that thing and get to the root cause, reduce the false alarm rate. And there are a lot of advancement going on right now in the industry, basically in those algorithms, to bring the more explainability and other things that makes it more robust. So that's the other dimension to that. The other dimension to do is, okay, so what question, if I detected something, if I cannot take action, so tying that thing to actionable thing, that's the another key area in the detection, primarily. So I will say these are some of the area. I can go on and on talk about whole day about some of these things, but these are some of the key challenges. These are all technical challenges, but also we should keep in mind the other aspect, non-technical challenges also, cultural challenges also. Even if you have these detection solution, you are using AI and machine learning, you have to change your business process. If you really want to be successful and you want to monetize it, you want to generate the value out of it, also you have to create the discipline of data governance. Like if suppose there are a lot of silos in all the businesses. Suppose some of the people who are running the operation, they are only worried about the sensor information and other. The people who are doing the maintenance, they will basically do the maintenance, they will record those things in the ERP system, maintenance management system, like Maximo, SAP and other. So there should be some discipline to capture that knowledge data and put it in a proper manner with the high data quality, so that you can get the maximum benefit out of that. So there are other dimension to that, more cultural change management aspect, basically to get the maximum benefit out of it.
Well, a few minutes ago, you mentioned the context being very important for some of the challenges, but I think you bring up a good point too, that the context of the person and their role in a business also determines what sort of result the data is going to be having. So getting all of the different people who need to understand different results of data to be able to agree on a solution is probably one of the bigger questions of moving forward with digital transformation and industrial Internet of Things.
Absolutely.
Now, technology is obviously advancing quickly, but sensors, as far as detection, I think that's what most of us think of as sensors. Those have been around for a very long time. So how is digital transformation? I think you mentioned this in a way with the temperature sensors, virtual temperature sensors from simulations, but what are some ways that digital transformation is impacting the area of sensors, whether that's the physical or virtual environment for sensing of processes?
Yeah, so there are different aspects. And I think in my career, like when I joined GE, I see that we have installed only very few sensors since I joined this whole journey. Like, because it is not easy, it is hard, it costs a lot of money, there is high reliability is required. Like, we did the blade health monitoring sensor, that was the advanced sensor, which was measuring the vibrations of these blades. And for 24/7 application, that's the key thing here. You apply these sensors quite a bit in the test facilities, like we are in the manufacturing another place, but just for that test, it lasts only for few days or few hours. But here you are doing 24/7 monitoring, where you are measuring 6 mils of the vibration of the blade, which is rotating with the over Mach speed. Like, it is over the wind sound, more than the sound speed. Basically, it is rotating with that kind of the speed. So there are not many sensors, and then there are only few sensors like combustion dynamic sensor in the gas turbine, or which is measuring the pulsation, which I have seen in my career so far. So you are exactly right. There are sensors are still same. Only we are adding few more sensors, basically in the on the asset. But there are a lot of other sensors which are evolving, like camera system. That is becoming a very key sensor nowadays to monitor. Like, we used to take a lot of round in the plant, go there, look for leakages, listen for sounds. A lot of those things are getting now, because of the IIoT solutions. Another, camera is becoming a critical sensor. In fact, we are using in some of our old facilities using camera for measuring the digital gauges. Like, we call it digital gauge, these are analog gauges. We are able to find out, hey, this pressure is here 110 psi, for example. We are able to do that, so that it is basically making a lot of things automated, and you can automate these rounds and other things also in the plant. That's the one dimension. But if you look into the overall, the technology, how it is evolving, uh, there are many things has happened in last 1 decade. First, connectivity to these control system, to these devices, and other massive scale. It was there in the past, but massive scale. We can now collect the data, acquire the data, ingest the data. There are a lot of technology like 5G and others are also evolving, which will further improve this capability there. Bandwidth has improved so much to transfer the data from local systems to the central system in the cloud. uh, Things have, security side has become pretty good nowadays. Like, security has evolved significantly. You can do not just single one way communication, but two-way communication you can do. That's why you can close the loop also in that space. The cloud is the transformational on the compute side. A lot of services which we were doing custom made, nowadays a lot of things are available which are interoperable across. There are in the protocols or whatever I can think about. These capabilities has ingest, we are able to ingest the data in a scalable manner, process the data in a very scalable manner using some of the technology like containers, which are virtualizing. You can deploy the solution very quickly, rapidly at the edge as well as cloud. So, and then advancement of these all the AI and ML techniques technologies basically is bringing a lot of value actually. So I do see significant transformation in last 1 decade actually in this space.
And one of those sensor options, or the data detection options there, with a camera being able to detect the position of a pressure gauge, and I imagine that camera could then be applied to a whole array of pressure gauges with the right conditions. Do you find with those kind of availability of data collection, whether we call them sensors or cameras, is it common to bring older facilities up to modern Industry 4.0 standards, or is this something that's really only available for brand new installations?
Oh no, I think some of those requirements are actually digital gauges and other are for the industry, where you have the high pressure lines and other things, and there is no way for you to instrument anything new right now. Like, you can always go to the modern transmitters and other things, but you cannot do that many places, like, because of the cost, because of other regions. So those are the places you can automate in this way also. That is totally different way to do the things. Uh, but that is the one dimension, is the sensor dimension. But I want to also talk about how the digital transformation is going on. I'm seeing a lot of customers are moving from to the modernization because of the rapid change in the pace of change in the industry, because of the regulations are changing, decarbonization is driving a lot of change, all the geopolitical things are driving a lot of change. So digital technology is the only technology which is going to help in this journey, where you can adapt very quickly, rapidly, with the power of the data basically here. Like, so So that definitely is one of the key drivers. So one thing is, okay, if the facility is too old, then you have to make your CNI system also. This is the phased approach. Like you have to make some changes, not everything, but something you can change there. Then the in the previous decades, the lot of utilities had created their monolithic custom architecture, IT infrastructure, basically. Now, because of the pace of technology, which I just talked about, several technologies, it is becoming more standardized, not custom. It is becoming more interoperable, working across the ecosystem. Many players can work in the same ecosystem, different vendors. That is enabling that. It is very modular in nature rather than in the monolithic. So I see that a lot of investment is going into making the modernizing that IT infrastructure in the plants as well as in the central system. And then we talk about the cloud afterwards, like when you can transfer the data another, then in the cloud tons of the things are available. A lot of things are on the compute side that is provided by the companies like AWS, Microsoft, and others. But at the top of that, the companies like GE are providing a lot of application platform to do asset performance management, operation performance management, and many other applications, actually, which are off the shelf, where there is not too much customization is required. Very quickly, rapidly, you can get the ROI from your investment, essentially.
I know that subject that you talk about flexibility as compared to some of the older, more monolithic type of architectures, custom designed. I know that's one of the main selling points of some of the data-driven applications, is that it's so modular and flexible. And I know here in a few minutes we're going to talk more about that dynamic optimization from this industry. But I think this industry in particular is a bit different than some other forms of manufacturing, in which prediction is often more about failures and maintenance. But what are sort of some unique situations where prediction is important in this field of energy production and generation?
Yeah, means I can talk so many things on this prediction side, like the whole generation plus transmission and distribution, all these areas, like these are the critical infrastructure industry, essentially, which is very critical for the society here. So think about these assets are operating in these are the assets which are not only generating the power, it is also generating the revenue for our customers, basically, like if you think about. And these are operating in the micro and macroeconomic environment. These are operating where the weather and climate is changing rapidly, as well as these power output depends heavily on the environmental conditions, like your ambient temperature. If it is renewable generation is growing a lot, it depends upon the wind speed. Solar, it depends upon the irradiation, even if one cloud cover comes. So how to predict, first of all, the generation, how much you are going to produce? That's the one challenging problem for renewable. For power generation, that is not that much of challenging problem, but still you are losing a lot of things on the table if you are not predicting that accurately. Like we put a lot of conservation, like whenever somebody is predicting what is the capacity of my combined cycle power plant, we fuzz a lot of things at the top of your prediction, so that we are not making wrong decision whenever we are bidding our power plants in the where we are dispatching the power plants. What predictions can do, the technology has improved significantly by bringing some of the physics approaches, which are more thermal, heat, and mass balance, combined with some of the capabilities of the machine learning, where you are using some of the neural network and other technologies. You can predict the capacity with very high accuracy, so that you are not losing the value which you could have bid that extra capacity there, but you are putting the margins. You can reduce your margins, you can even bid your capacity much more, and you can get monetize it much more. This is just one example. Wind is how much I am going to produce from this wind. That is very critical, because in many scenarios your cost price is negative also, and then you are losing the money right then making the money. So the prediction, there is some requirement, regulatory requirement, other things making those kind of the prediction in the short term. Even in the long term, you have to make a lot of those predictions there. If you are talking about transmission and distribution grid, as the things are changing drastically in many countries, we are seeing in the UK, Australia, and other places where the renewable generation is really getting very high. So you don't have any more inertia in the system, which is run by these big mechanical rotating machineries like your combined cycle gas turbine plants or coal plants or nuclear plants. These are being run by the power electronics, the grid, like the solar static, as well as your wind turbine. There is a lot of power electronics based things there, non-synchronous kind of the generation. You have to predict the inertia. How much is the inertia in the grid, so that now you can take the action, because low inertia grid, very challenging to operate. So we are seeing tons of the prediction use cases actually beyond just traditional, at least in the power generation, transmission, and distribution industry.
And I think that speaks a lot to the point that we were just talking about with data collection, which, again, most people might think of sensors when they think of data collection, but you mentioned so many variables there that can't be sensed because it's not a parameter of the system in play currently. It can only be done through prediction of looking at a lot of other variables that would normally be very difficult to detect.
Exactly. Fully agree on that front. Like, think about the EVs, like electric vehicles are growing. You have to predict the traffic pattern, because this load is also changing now. Location is changing of that load. So when the people are going to switch on, switch off their devices, because the lot more electrification is happening with the heat pumps and other things in the future, then you need to predict some of those behaviors, so that you can now balance the supply and demand properly in the real time. It is both for generation folks, they want to make more money, then they should have the availability of their resources, how to make it available, as well as basically for the transmission and distribution grid folks, who are basically going to orchestrate these resources in the most optimal manner, essentially to bring the affordability for the general masses, as well as have the high reliability and resiliency, so that anytime when I switch on, I have light, basically.
Now, if we move to maybe a little bit more technical detail and looking at some different models of how prediction is used for different areas, you mentioned the idea of this 24/7 operation, or more of a prediction for a continuous operation model, versus the way some people might think about prediction for a specific asset is looking more about end of life prediction, or predicting the useful life of a machine. Are there differences in the consideration between continuous performance versus end of life modeling for prediction?
Yeah, means there are definitely differences, and even in the continuous remaining useful life, the whole asset management, whatever we do, life management we do. Let's take the example. Let me give some brief history, like how the maintenance philosophy has evolved. Like, we started this whole journey with the run to failure. Earlier, we used to just run the equipment till the time it fails, because we didn't have much knowledge, no data, nothing. Long back, like 70s, 80s kind of time frame. Then this whole reliability centered approach, RCM approach started, where you are collecting some data, like, hey, this is the insurance kind of the policy, like what is your age. So in this particular case, okay, I have the hours, start, trips, that kind of the counter information which we get from our control systems, basically counters, essentially. Like, so based upon that, you are bringing some demographic based model. This is the population based model, fleet level model, that gives you the insights that, okay, I can run these equipment from this interval range, basically I can operate. And that's what you came with the reliability center approach, essentially. Then you move to the condition based maintenance approach, where you are now taking the inspections on regular intervals. Every year I am looking the boroscope, sending the camera, and then finding out how is the part. So that's the condition based approach. Then we move toward the PHM, prognostic health management approach, where I am continuously collecting the data. I am finding out how much damage I am accumulating every single day, depending upon different operating condition, whether I am operating peak firing, I am doing part load, I am running cooler, or I have water injection is on, or I have now, even to the extent of what I'm ingesting, because we are sucking a lot of air in the compressor, for example. Then what is the climate outside, and based upon that, I'm doing that prognostics. The last stage is the digital twin capabilities, where I'm now not only just looking these continuous predictions from the real data set, but I am getting a lot of contextual information also, what's going on, to get the 360-degree view, and also doing the continuous learning. Like, I am continuously adapting these models as I am learning more and more, so that I am getting much better precision in my prediction. So that's where the evolution, and that's what this whole thing, moving from interval based to the continuous prediction, kind of the fleet based, demographic based to the continuous prediction based. the technology has evolved significantly, and that has been enabled because I can aggregate the data from multiple places, I can visualize the data, I have many different kind of the methods or I can apply. So that has essentially enabled some of those things now.
Now, this is also something that you mentioned a little bit earlier, is that energy is more of a network-based approach. So rather than individual facilities looking to just increase the performance of their own facility, there's multiple things at play with energy. How do large, I might say, crisis type events, whether that's a weather pattern that's unexpected. I mean, all the time we see things like heat waves and cold cycles in the weather, geopolitical conflicts, things like that. Are those types of things that that power companies must worry and concern themselves with in this prediction phase?
Absolutely, absolutely. If you look into the statistics, like if you go to NOAA or Climate Central and other places, you will see between 1980 to 2020, there had been 285 severe weather events that costed US economy $1.85 trillion. If I look into just last 5 years, 2015 till 2020, just 5 years, $600 billion, that is 30% of last 40 years I'm talking about, just happened in the last 5 years. And another statistic, you will see that these the distance between these events, it was years, but now these $1 billion disasters are happening on monthly intervals. Like what is going on in the Florida, what happened in the Northwest, uh, basically in the California and all the wildfire and other. I personally live in the San Francisco Bay Area, and we have seen the PSPS event. These are power system shut off events, basically from the safety point of view. Whenever the temperature is very high, the wind, it is very dry environment, wind speed is very high, then we are shutting off the power, otherwise it will cause the wildfire essentially. And then it is causing huge amount of the cost to the society and businesses, like so. We are seeing more and more the trend in this area. So there are a lot of solutions today, not only just for the transmission and distribution, even generation. What happened in the Texas, uh, the snowstorm which we saw basically a couple of years back, that was brought the Texas grid at the brink of full blackout, very close to that. So now, if I talk about some of the capabilities which are required today to deal with some of these kind of the events, first of all, planning kind of applications, like where you are basically able to, in the real time, this is the dynamic planning you are doing, like because weather is changing, in this extreme weather is changing whenever these things is happening, either it is wildfire or storm. So how to you first predict, okay, this is the way the things are changing, then you then estimate what is the risk to my asset. Like take the example of transmission and distribution. These are the circuits which are getting impacted. Now you basically say that, hey, what resources are available in my grid, how to optimize that, how to take the outages in such a way that minimum amount of the people are getting impacted, because otherwise business is losing a lot of money, lot of community will getting impacted. So we are building the solution, where we have built the solution actually called Storm, that is your smart transmission outage and restoration basically system, where we are able to predict these things, we are able to do the planning for the outages in the real time, as well as we are able to restore the things by applying the closed loop control, how you do the switching so that you are minimizing the impact. So a lot of these kind of the applications are definitely currently required, from the planning till long term planning, as well as at the real time when these events are happening, so that minimum impact is there. How you will set the load, you can't set the load longer time for one community, because this may impact that community. So you do the rotational load setting. You are basically disconnecting the supply for few minutes or couple of hours in one place, then switching to the next. How to do in such a way that you are basically not causing big disruption to some particular community or the business. So all these things are being done. It is very difficult for the humans to do this, because you are getting the data from multiple sources. How to do that in the automated manner, I think a lot of these IIoT or these controls capabilities, intersection of those, are bringing all those dimension and element. Same thing is applicable for generation also, like whatever we saw, because of the cold weather, a lot of generation was not available. So how you will even predict some of those things, and how you will prepare for those, Even the whole aspect of predictive maintenance, even your units are available, your there will be no outage when these things are badly required. These are prepared to act in this kind of the emergency situation. If you have these kind of the predictive maintenance kind of the solution, then in that case you are keeping the high availability and reliability of some of these kind of the assets. So there are multiple dimensions to prepare for these kind of the extreme weather event, which are not going to come down, those are going to grow with time.
Keynote speakers and live sessions for Control Automation Day are brought to you by Mouser Electronics. As your design fulfillment distributor, Mouser is your authorized source for millions of components from thousands of leading brands. Come discover, design, develop.
And I think talking about that is a perfect segue into kind of our third part that we're going to talk about here, because we've talked about the data collection and we've talked about some of the models and events for prediction, but then probably the more important part is the result, the dynamic optimization. And so I'm just kind of curious, what are some of the different modes of optimization? I think for most people, when they think of, if they've been in industry for a long time, most of the optimization happens by an experienced engineer observing and knowing from experience how to optimize something. But what is the difference here now with automated optimization following the data collection and prediction models?
Yeah, I think we can say that there are two kind of the optimization modes here. Like the first optimization mode is where I can make the predictions, and from that prediction I have real time optimization, and that real time optimization is giving me optimal set points. This is supervisory control layer, basically. Like that is giving me smart set point, that is collecting the information not just from sensors, it is collecting the information from weather, it is collecting the information from price, it is connecting the information from what's going on with my current asset health, and then running the optimization, and then feeding that smart set point to control system to run the closed loop, basically. uh, the scale is much faster scale we need to do it, because it is the closed loop control, there is no human in the loop. This is the real time, basically. So and then you should have the other requirement is the convergence. Your optimization solution should converge, otherwise you are not able to close the loop there. So I think some of these kind of the things are definitely required for real time closed loop control and optimization. We are doing some work. I will just give you an example. Let's take the example of the wind turbines. In these wind turbines, you are these every single wind turbine has different kind of the unique control setting required if you really want to run it optimally. It should have the same pitch setting, pitch angle, which basically moves these blades just like plane wings. And then you have the yaw, that is completely moving the face of the wind, like that is the complete wind turbine we are moving. And then you have the tip speed ratio, like the wind speed, basically turbine speed. So these are the different set points, and that varies. And not forget about seasons, that can vary from day to night. If you look into the wind shear patterns, different stratosphere, it changes from day to night. If you are keeping the same control setting all the time, then you are not optimizing. So what we are doing basically as a part of our ETPO, that is this enhanced turbine performance optimization in the wind turbine, where we are taking some of the physics information. That physics information is bringing the boundary conditions to ensure the safety of the controls, integrity of the structure. And then we have the machine learning model that is continuously learning, basically. And that is basically providing the optimal pitch setting, yaw setting, tip speed ratio setting in the real time to regulate this so that it is always running in the optimal condition. What it does, it is giving you over 1% of AEP. This is annual energy production. It is increasing the production, basically. So these are the kind of the closed loop application. Same thing we are doing in the turbine, where you are basically doing monitoring the combustion dynamics emissions, because those changes with the seasons, with day and night, with the temperatures and the degradation of the machine, and you are dynamically predicting those and closing the loop with the optimization, and then you are minimizing that. And there also we are applying some of these neural network combined with the physics based kind of the approaches, essentially. So that's about the closed loop. Now talk about the other kind of the mode where the humans are in the loop, basically. I can give you one example that can be applied both in the closed loop as well as in the open loops setting where the human are in the loop. Let's take the example of, we talked about detection problem, early warning prediction problem, where I'm detecting the things, and once I detect the things, then I am sending the alert. It is automatically going through your the email is going, or automatic case is getting created. So these are the workflow management tool, ERP system. Those are the kind of the system it is connected, and then humans are looking into that, and based upon that they are either solving the problem themselves in the 24 by 7 monitoring, or they are escalating to the level 2 kind of the experts there, and that person can say that, hey, this is the problem, these are action needs to be taken, then call the site personnel. That site personnel can take the action, and then what maintenance was done, feedback to your ERP system. Now I have closed the loop, but a lot of humans are in the loop, a lot of ERP kind of the systems are in the loop. The workflow management systems are in the loop, basically in this whole thing. So it is primarily kind of the decision support system. I can do the same thing in certain other situation where I can make some prediction in, suppose, gas turbine. I can predict the lean blowout event, that is the combustion instability, that is very fast phenomena, and I have done the detection. But now I can feedback that detection to the closed loop to change the gas control valve setting in such a way that it is bringing that gas turbine away from that instability essentially, and I can avoid that trip of the gas turbine basically, for example. Like, so this is the same detection problem but applied into two different closed loop setting. One is the closed loop control setting, fast in few seconds, or the second one is basically that may take even days, hours, basically to make those kind of the business decisions. uh, so those are basically, I will say that these are the two different remotes there.
Now, is that a different kind of technology that's used when we're applying a closed loop system to a business practice where the business decisions are being the main point of concern versus the control system decisions? Because these are two different groups of people who are ultimately responsible for either managing the control system or the business practices. Is it the same set of tools that are used, whether that's offered by GE or other manufacturers, or are these two completely different software sets that must be handled separately?
Yeah, there are some commonality and there are some differences there also. Like, it totally depends upon use case by use case basis. So suppose I am applying the controls optimization technologies for real time control, then definitely the suite of the algorithms, it can be same for your cloud kind of implementation, but you need to run it with much faster, because it needs to converge in seconds basically to close the loop. And in some cases you are running in the millisecond. So definitely there are differences. Closed loop control is more automation kind of the community. You have to run the things on the edge. There are it needs to be also very robust, because I mentioned that convergence safety aspect. If you make any wrong decision, then turbine component can get damaged, or any other equipment can get damaged. Those are expensive things, because there is no human in the loop. So definitely there are some optimization methods, nonlinear optimization methods, or you linearize it, you make it faster to run. If you are using some machine learning technologies, then you want to bring in more of assurance, first data assurance, and then other assurance is model assurance here. Like, we call it humble AI. AI has humility to say that, hey, I don't know, and if it is going outside the competency region where I trained my model, and now because of the operation condition is very different, I have never seen this kind of the novel situation, then in that case it should have ability to say that I don't know, I want to learn, provide me more simulation, more other data source, and then give back that control to some default system that is ensuring the safety or the conventional system. So definitely there are some differences, but there is a lot of commonalities also, how the connectivity is happening on the data side. Some of the new the architectures are evolving on the algorithmic side, on the machine learning another side, if we are using the machine learning kind of the solution. So it depends upon the use case by use case basis basically.
Now, if we could take this conversation and just kind of point it a little bit more specifically towards some of the audience members that we have on our site, a large number of which work in energy production. they often have concerns over certain things. And some of these things can include things like maintenance intervals for turbines, synchronization and sharing of loads with generation, temperatures, vibration, and thermal efficiency, all of which we've discussed certain aspects of that. So to address some of those specific points, would you have any examples of, in some of those cases, how can some of these IIoT solutions with prediction and optimization be used to ultimately to optimize and reduce the risk of downtimes, failures, and inefficiencies in some of those areas of concern?
Absolutely, absolutely. Let me give some example because this is very relevant for the community, like maintenance interval you mentioned. Like, so maintenance interval. If I come into any combines, let's talk about the combined cycle power plant or even coal plant. So combined cycle plant, my maintenance interval is primarily driven by my gas turbine, hot gas path system, basically related maintenance or combustion inspection or major inspection. And many times you are putting a lot of efforts on the turbine side of the part. Like, okay, there are intervals like GE kind of the companies has provided based upon the experience on the fleet, based upon a lot of sophisticated algorithm analytics which we run for life management side, and based upon our design limits and other, we say that, hey, this inspection interval, apply that policy across that. But there are a lot of other things. If some controls engineer wants to do balance of the plant, I'm taking the outage in the gas turbine, they want to run some kind of the inspection there, but you are not inspecting everything at that time of the outage. What we can do, basically, we are continuously monitoring the BOP different assets. We are also trying to understand the health of those assets and take the opportunity maintenance. Whenever I'm taking some outage on the one part of the system, and then other system is down, then I can basically do the opportunity maintenance at that time, so that this system is not down at that time whenever it is required. And then this is the best use of the time from the controls engineer or other community there. So monitoring the whole system is critical. Even on the interval side, like maintenance interval side, let me give you one other concrete example of boilers, for example. These boilers are essentially, we do the inspection on regular interval to measure the thickness of these tubes in these coal-fired boiler, for example. And if suppose this tube becomes thinner and thinner, then it is beyond the mechanical integrity limit, then it will rupture after a certain time. If it ruptures, then tube failure outage becomes very long outage, and it causes a lot of downtime essentially. Like, so we have built some kind of the solution there, where you run some CFDs kind of the analysis, computational fluid dynamics analysis, finite element analysis, to understand, because there are not sensors to understand the speed in that region, like how the wear will happen in anything, because these are the ash particles which are crossing, which are rubbing with these tubes and causing that, and it depends upon your speed of the air there, ash particles, and many things. So you are running some of these simulation models, uh, then coming out with the what should be the speed in this region, of the wind speed or the air speed there, and then based upon that you have the wear prediction model. All those things you can create some, running the physics simulation, converting that simulation into some of the meta model that can run in the real time kind of the environment. So you are leveraging the best from the both the word data as well as physics. You are taking the information from data, real time data, which you are getting, hey, this is the my load at that time, this is my steam flow at this time, this is my airflow at this time. Based upon that, you are predicting this will be the wear at this time. And then I'm collecting the inspection information on the regular interval, that I'm calibrating my model. I'm saying, hey, my prediction was XX millimeter thickness, but the thickness was YY millimeter. Then I have difference here in the prediction. I can use that inspection measurement to calibrate that, and then use it for the real-time prediction and making the decision when should I do the change it these parts, or do these inspections or replace these tubes, so that, or extend it to the maximum interval, so that I'm maximizing my, basically the investment here, or minimizing the overall cost. So these are different kind of the scenarios on this particular thing. Other example, you talked about the thermal efficiency. The community is talking about that. I gave so many example of performance monitoring, where the micro macroeconomics is primarily driving that. You can run several kind of the algorithms using the collecting the sensor data, combining that with the basically your price, your price forecast, your load forecast, and other things, and to make different kind of the decisions. You can use the performance monitoring information, thermal efficiency monitoring for diagnostics purpose also, where that is becoming a virtual sensor. And that virtual sensor now I'm using to make the better prediction. And I have personally seen, because I have experience in working in the aerospace and other industries, if you combine the physics model, these performance models, along with some of my other machine learning kind of the approaches, it is giving me better capabilities, better lead detection time, lower false alarm rate, better root cause analysis diagnosis capability essentially. So I think definitely I'm seeing a lot of these applications, whatever you mentioned, whether it is thermal efficiency, inspection interval, or even vibration monitoring. Many of these applications, IIoT is, and then some of the AI capabilities are significantly getting much more accuracy, precision, and value to the industry, basically.
And something that I'm hearing through several of these discussions now is the fact that the models can be improved by the combination of both the models that can predict to a certain degree of accuracy, but then with unknowns, it's compared against how the actual result is, and through that collection and continuous improvement of data, those analysis and predictions are only going to get more and more accurate as they're verified and taught essentially against the predicted outcome versus how well did it match what actually happened.
Absolutely, that's the power of doing this continuous learning. And that's the way, if you look into the consumer part of the world, where every single day your search engines are becoming improving, and it is sometimes very creepy that they will give you the ad what you are thinking how this is basically telling me. Even in the self-driving car area, like this assisted driving is continuously improving every single day. Basically this has all the learning loops, and these things are getting better and better and better every single day. I think same thing is going on in this our industry also, and we are at the cusp of that kind of the transformation right now, I would say.
And here, as we move to the future is always a little bit harder to predict. Nobody's ever been able to tell what's going to happen in the future. But if you were to be able to make a prediction, what would you say are some of the future challenges that people are going to have to consider, particularly the engineers in our audience? What are they going to have to consider in efforts of improving themselves and their own skills, but also the performance of their facilities? What are some of those challenges that you think they're going to have to pay particular attention to in the future?
See, I think some of those things we already talked, but I will say yes. I think it is very hard to predict the future, but there are few things I am very certain that we can predict today. One thing is your extreme weather events are going to become worse. We are seeing that already. So that is that, and then preparing for that and having the planning, optimization, dynamic planning, optimization, controls capabilities to take care of your extreme weather events, both generation, transmission, distribution, all that area is happening. Second thing is basically because of the climate change, again, because of the decarbonization goal, policies are changing. We are going toward the zero carbon. A lot of countries are putting the regulations as well as targets, those goals there. More and more renewable generation is going to happen. So that energy mix is changing, and that is definitely impacting this whole non-renewable as well as renewable generation mix. And that is definitely going to happen, and how to prepare. And all these renewable generation has a lot of uncertainty, lot of variability, and how to tackle that, that is required. Third phenomena whichever is going on, the whole decentralization of the energy. Basically we have rooftop solars in our home, that's going to grow. We are using a lot of electric vehicles, so and demand of energy is definitely going to grow. Yeah, there will be some efficiencies also we are gaining because of the smart homes and other things, but still uh, in the next 2 decades the energy is going to grow almost 35 to 40%, 50% growth is going to happen in the demand side. So that is definitely going to grow, but it is posing a lot of also another technological challenges we need to deal with, like decentralization of energy. A lot of DERs are there and other, and how to tackle those. Even for the conventional generation, this whole generation mix is going. uh, you need a lot of flexibility, even in the combined cycle plants or other generation sources, because of the renewable generation is intermittent, uncertain, and how to basically manage your generation mix by bringing a lot of flexibility services. I think that is not going that is pretty much the prediction I can say that it is happening right now. Other thing is that this whole technology like AI, it is the only technology today is exponential technology. Like it is able to AI is creating AI basically like soft. It is writing the code. Like take the example of this whole Chat GPT, whatever is going on, or
Yeah.
Codex, where it is able to generate the code. So this is the technology, exponential technology, which writes the code to make it better and make it efficient. That is not going to come down. That is going to improve. Now the question is how to leverage and exploit it, so that you are doing basically you are leveraging all that capability for your advantage. One thing I will say that, hey, the people, the engineers who are going to use some of these exponential technologies like AI will never replace engineers and scientists or this community, but AI will replace those engineers and scientists who are not going to use these AI technologies basically. So that's the other critical aspect I think we need to think about basically.
And this, I believe, is a perfect time to have this discussion about IIoT, as just recently we've seen the explosion of some of these. Is really our purpose is to educate the engineers. What can they do to improve themselves? And I think you've addressed that very well. With our remaining time here, I just have a couple of quick, more casual questions for you.
Yep.
And the first question is, what is your very first IoT related project that you ever worked on? Was it something that was a real world project for a career, or was it something that you just did for fun, for learning?
No, it was my real world career project actually. When I joined GE Research, I after industry basically, then my first project was I was tasked basically, hey, you have a lot of domain knowledge, you comes from the controls and all this background, and you have decent analytics knowledge. Develop the algorithms to predict the gas turbine failure trips. Can you predict the trips in advance so that I can convert these downtime from unplanned to planned essentially, or take the basically some of these outages in a gradual manner so that it is causing less impact on the turbines, because if it trips, then it is causing a lot of life loss also to the turbine, and it is unplanned, so you are losing a lot of money, our customers lose. So that is the first project which I did. I still remember that I was predicting the thermocouple related failures, because sometimes the thermocouple fails and then controller thinks that, hey, these are the combustion issues and it will cause the trip by thinking it is combustion problem, but it is thermocouple problem. So I had to distinguish that. And the work whatever I did at that time, we were collecting the data from on-site monitors who are connected to the control system. We were getting the data. There was no cloud at that time, but we had a central system in our Atlanta, basically M&D center, where we monitor large amount of the fleet actually. So there we were collecting the data, and we were learning from that data, building some of the statistical signal processing as well, including machine learning algorithms actually, which we built to predict these failures. Same thing I did for gas control valve failure, and many other the top Pareto, whatever the trips we were seeing in the fleet, building the capability for that. So definitely that was my IIT, and I'm really proud that still some of this capability which I built at that time, in some form and fashion, a lot of improvement has happened, but still those are being used for 24 by 7 monitoring and saving some of these kind of the failures for our customer. And I published the paper out of it in the peer reviewed journal, as well as filed 2 patents in that. So definitely that was my first journey into this IoT real world application.
Great. Very last question. We have quite a few either very young engineers or students who are just getting started with a career. If you could go back and tell yourself one thing during college, or go to one of these young engineers and tell them something just as they're getting started, whether that's advice or ideas, what would that one piece of advice be?
See, I will say that in the colleges, generally, interdisciplinary education is very, very important. Like I will say, if you can collaborate with other disciplines, other, not only suppose you are mechanical engineer, you are partnering with the control. Even in the curriculum, there should be some interdisciplinary projects and other things. which helps in bringing that system level perspective, system level view. Specifically, this community where there are a lot of controls engineer, it is the system level play where you are bringing multiple disciplines together. I think that's the one thing I would like to change. Other thing I will definitely change, uh, as I mentioned earlier, like because of this data is becoming a basically very hot topic and critical technology, which is causing a lot of transformation. And in some of these colleges and some of the students, even if those are not offered as a part of their discipline, uh, they should take some of the courses like machine learning or data science introductory courses, because that definitely gets you different perspective. Then you think very differently, you apply various things whatever you are learning in your disciplines, whether it is electrical engineering, mechanical engineering, computer science, chemical engineering, in very very different way, and you can get exponential value of your degree basically in that. um, so having some of the data science machine learning course, and at least learning some of the modern programming language like Python, for example, that is uh, I'm suggesting Python, because in the controls community or electrical engineering and other, we use different kind of the language like MATLAB, for example. It's very popular, but some, because this is very good for controls kind of the application, but learning some other languages, because a lot of libraries, open source libraries, a lot of innovation whatever is happening, you will have access to that, and you can manipulate the data in a different way, and you can apply your discipline knowledge, and you can get the significant benefit out of it. So I will definitely suggest to have that interdisciplinary kind of a nature, as well as bringing some of the data science and machine learning kind of the capability also. And I'm seeing that a lot of, I am really encouraged to see. In fact, I was chatting with some of the UC Berkeley professor few years back, and then he was mentioning that, hey, we have started that kind of the journey, and basically where we are offering these kind of the courses. So I will highly recommend the students to take those courses to get the significant benefit from their education.
Well, thank you very much for this discussion. I know I've learned a lot about both from your story and about the adventure of energy production and some of the challenges and the solutions that IIoT is bringing to this industry. So thank you so much for being here with us and sharing your experience and your knowledge on the subject.
Thanks, David. I think it is my privilege. Thanks for inviting me and sharing my insight for this fellow community, because I was one of those many years back, basically. So, but that is really, thanks for inviting me.
And thank you to our audience for joining us today for this keynote sponsored by Mouser Electronics. And once again, our sincerest thanks to GE Digital and to Achalesh Pandey for sharing his time and experience with us. We hope that you will visit the virtual vendor booths and watch the other keynotes and live session events, all of which will still be available on demand after today, so that you can share the experience with anyone who may have been unable to join us live. Thanks again for joining us for Control Automation Day 2023, and we look forward to seeing you again very soon.